There are three main types of context-aware recommendation systems, or CARS, algorithms. There's contextual pre-filtering, contextual post-filtering, and contextual modeling. Let's go into more detail for each type. For contextual pre-filtering, we start with our user-by-item-by-context tensor that contains ratings. In traditional collaborative filtering recommendation systems, we have just a user-item interaction matrix that contains ratings. We then apply a filter on our context before the traditional user-item interaction matrix recommendation system, which is why it's called pre-filtering. As an example of this, imagine we are looking at movie theater tickets online, and we hope to go Thursday after work. Therefore, the algorithm will filter out all movies that don't have the time dimension of context equaling Thursday. However, we need to make sure things don't get too specific. For example, this user wanting to go to this exact theater on Thursday with a friend from work where there will be special effects glasses to wear during the movie. That is a really specific context, and there are probably going to be sparsity issues. We can also use context generalization, where instead of saying the user wants to see a movie on exactly Thursday, it's a blend of Thursday and weekday, for instance. After the data has been filtered by context, the data is once again our usual user-item interaction matrix, which we can use in our traditional collaborative filtering recommendation systems. Note that the contextualized data is filtered by certain dimensions of context, so it's actually a subset of the original data. Our contextualized data now goes through a traditional two-dimensional collaborative filtering recommendation system. This is a big plus because there is no need to develop and implement new algorithms to handle this multidimensional context in our input tensor. As we've learned, our recommendation system will simultaneously learn the user and item embeddings that we can then use to make recommendations. Next, as we learned in Module 3, we now apply our user vector to the embeddings learned by the recommender to get a predicted rating for each item the user hasn't already interacted with. Lastly, for contextual pre-filtering, we return the top K item recommendations to the user. Many different contextual pre-filtering algorithms have been developed. Because this is contextual pre-filtering, they all are different methods of representing and splitting the data so that it can be used in a traditional two-dimensional recommendation system. We'll take a deeper look at item splitting, user splitting, and the combination of the two with user-item splitting. We've talked about how context can change our perception and thus sentiment of the same item. Therefore, it isn't unreasonable to come up with a data representation model where we split items into item context pairs. Here's an example of a user item context table with the associated ratings. This example only has one dimension of context, time. Let's briefly analyze it with inspection. The first thing we might notice is that there are 4 users and they all watch the same movie twice, but at different times. Looking at the ratings, we can see that there is a big block of very high ratings at the top. We can also see a large block of low ratings right below. This also looks really strange. What can be causing this? Let's check the context. Well, there's the difference. All of the high ratings are when the movies were watched on weekends, and all of the low ratings are when the movies were watched on weekdays. Because there is such a significant difference of ratings between the two contexts, with everything else being equal, let's split the item into 2 item context entities. There we go. As we can now see, our items have been stratified across context. They are blended together. This functions as if the item was actually multiple items. This is easy to see when we have a small toy dataset like this, but how do we do it for much larger and more complex datasets? We simply can use a t-test on 2 chunks of ratings and choose what gives the maximum t-value, and thus the smallest p-value. There's a simple splitting when splitting across one dimension of context, and complex splitting when splitting over multiple dimensions of context. Complex splitting can have sparsity issues and can have overfitting problems, so single splitting is often used to avoid these issues. There is also user splitting, which is extremely similar to item splitting, except now we split along user rather than item. If we arrange our data now to be sorted by user, our user item context table looks like this. With user splitting, we are now splitting along users as if they are separate users interacting with the item. Users are basically now user context pairs. As the name suggests, user item splitting is splitting along both dimensions and blending context into users and items. There's a new dimension of context, location, added to help make this example more clear. To see what we have done with splitting, the context columns are still remaining. Here we did two simple splits, a user split along the time context dimension and an item split along the location context dimension. Removing the context columns we split along simplifies this table to this, where we have user time context pairs as individual users and item location context pairs as individual items. We can now send this contextually pre-filtered data to our traditional two-dimensional recommendation system.